Here we're going to see at the basic how we generate an AC voltage. An AC voltage is an alternating current voltage. And alternating because one time the voltage is positive and sometime the voltage is negative. So the voltage will change during time. That's mean alternating. Here we can see that we have a sine curve, but it could be any other curve form, and it doesn't have to be symmetrical around 0. But here, this generator generates sine curve, and it's positive and negative. When we measure the sine curve out here, we can see it is connected to a wire inside the generator, and we got 2 slip rings and brushes so that you don't twist the wires when we rotate the generator. The wire or conductor, here we can see there's only one turn. We could have many turns if we want that, and it is rotating in a magnetic field. We have the magnetic field lines from north to south, and when we rotate the wire in the magnetic field, we generate a voltage. We have to know something about an AC generator, because we have one term called frequency, and it is actually the number of cycles per second. So how many sine curves do we make per second? The symbol is lowercase letter f, and the unit is Hertz, Hz. This sine curve we also see over here, and we can see when we make one sine curve or one cycle, we have time we call periodic time, and the periodic time has the symbol capital letters T, and it is the time for one period. It is measured in seconds, and the relationship between frequency and periodic time is that the periodic time is 1 divided by the frequency, or reverse, the frequency is 1 divided by the periodic time. So when we generate this voltage, we can see we have a voltage raised to a maximum. It is when the wire is located right here, and when the wire is centered on the south pole, we have rotated 270 degrees, and we are down here, and we have the highest voltage again, but now it's just negative. So this generator, we generate one cycle, one sine curve in one periodic time, and it is when we rotate the wire one time. We can see on the x-axis, yes, we got the time, but also we have an angle, because we can see over here 2 pi. So this is 1 revolution when we measure the angle in radians. We can also measure in degree, and then we just start at 0 degree and end up at 360. I prefer that because radians, we don't know exactly, for example, the angle right here, but in degree we normally know something like it's a little bit lower than 180 degrees. And here we can see that we have that voltage increase, and for example here the voltage is reached to exactly this value, and it has taken this time, or we can say the wire has rotated an angle. Here we use theta, we can also use alpha. So the axis here, we can say for a given time or for a given angle, and we have the total periodic time, or 360 degrees. So the relationship between the angle divided by the total length, 360 degrees, is equal to the time divided by the periodic time. And this information we use later. The basic formula when we generate a voltage is that the electromotive force is change in magnetic field over change in time multiplied the numbers of turns of the wire. So if we want to increase the voltage, we can have some more turns. We can increase the magnetic field, or we can decrease the time, or it means that we rotate faster. Or we can say that the electromotive force is the flux density multiplied by the length of the wire, the effective length, this and this, and multiplied by the horizontal speed. It is because we can see over here, we only generate voltage when we cross the magnetic field lines. And the magnetic field lines go from north to south. And for example, when a wire is exactly here at 0 degree and is going upwards, we don't cross any magnetic field lines, so that the voltage is 0 right now. We can also see over here, at 0 degree the voltage is 0. Then we reach 90 degree and the voltage is positive maximum. 180 degree, then again we don't cross any magnetic lines, so the voltage is 0. And here again we again cross magnetic fields as a maximum, but now it is the south pole, so the voltage is negative, and here we have 0 degree again. So actually the speed of the wire right now, we have it here. We can put this vector into two, one this way and one this way. The vertical speed has the same direction as a magnetic field, so it doesn't generate a voltage. But the horizontal speed generates a voltage because it crosses the magnetic lines. So actually we have to multiply by the horizontal speed. We can see it down here. And if we look up here again, we can see that the horizontal speed must be the hypotenuse multiplied sine for angle of theta or alpha, because this angle must be the same as this angle up here. Because if we have the wire out here, we only got a vertical speed, so this one is placed here vertical. We don't have a horizontal speed. And when the wire is rotated, this angle gets higher and higher. And the horizontal speed, put it up here, we can see here we have a right angle triangle, and then the length for this one must be hypotenuse multiplied by the sine for this angle. So instead of horizontal speed, you just can put in the speed and then sine for the angle. This value, the speed of the wire, the length, effective length, and the flux density, we can put in to one value. That is the voltage, the maximum voltage, the maximum electromotive force. And it is located up here or down here. So basically it is quite easy to find out the instantaneous value for the voltage is the maximum voltage multiplied sine for the angle. Instead of the angle, we can say it must be sine for then the angular speed multiplied by the time. The angular speed, we know, normal speed is for example meter per second, but the angular speed is radians per second or degree per second for any given angle per second. And if we multiply by the time, we must get the angle. Probably you've seen many times that the angle speed is 2 times pi times frequency. That is also correct if we want to measure the angle in radians. We got 2 pi is 1 revolution, and then multiply by the frequency, we got the angle speed. We also can set, instead of 2 pi, we can say 360 times the frequency multiplied by the time. So here we also got an angle, and it is in degree. So I prefer this one because here we can keep our calculator in degree mode. If we want to use this formula, we have to switch to radian, and many times we forgot to switch back again. So I prefer exactly this formula, or this one, if we have, for example, the information about the periodic time instead of the frequency. We know up here that the periodic time or the frequency is 1 divided by periodic time. So instead of multiply by a frequency, we can divide by the periodic time. So here we have many formula how to find out the instantaneous value for the voltage. And we have learned frequency is cycles per second, and the periodic time is the time for one period or one cycle. And the output voltage depends on number of windings or turns, the power of the field, and the time we use to make the rotation, or actually it's the speed. So that was the basic of how we generate AC voltage.